Okay, hi guys. So in this lecture, we'll be discussing on energy. So let's get started. So we will classify energy into two forms. First, we'll be taking on heat, which is the energy transferred due to temperature difference. Okay, and second one would be work, which is P delta V. Okay, and we can write that dq would be equals to ms dt. So integration of dq would give us ms dt would be, so this implies q would be ms delta t. Okay, m is obviously the mass and delta t is t final minus t initial. Okay, we can also write let's see a constant c, which is specific heat capacity or specific heat. So it is specific heat capacity or specific heat. Okay, so units can be joule per gram degree Celsius or joule per gram Kelvin. Okay, and we can write q as c delta t. Okay, now we know that c is heat capacity, and that would be equals to q equals to ms. So as q equals to ms delta t from the first equation and q equals to c delta t from the second equation, this implies that c equals to, which is heat capacity, is equals to ms. Okay, okay, so c can also take two forms, which is cp, which is nothing but heat capacity at constant pressure, constant pressure. Okay, I think by the way I wrote by mistake, this is not c, this is s, a constant s we are seeing. Okay, because we took s here. So this s we are talking about, this s is specific heat capacity or specific heat, and this c is rather only heat capacity. So the units of c can be joule per degree Celsius or joule per Kelvin. Okay, and heat capacity is nothing but mass multiplied with specific heat capacity. Okay, so heat capacity can take two forms, which is cp and cv. cp is heat capacity at constant volume and cv is heat capacity at constant, so sorry, cp is heat capacity at constant pressure and cv is heat capacity at constant volume. Okay, now we can write du as rather we can directly write du as ncvm delta t, which is dq at constant volume. Okay, so we can integrate into ncvm dt. So delta U would be Q at constant volume, that would be equals to NCVM delta T. Okay. Where U is, you can write U as internal energy. And let's define next dH, which is change in enthalpy, which would be dq at constant pressure, that can be written as ncpm dt. Just integrating the same here again, so we would be getting delta H, or change in enthalpy, which would be equal to heat transport exchange or exchange at constant pressure, that would be equals to ncpm delta T. Okay, so H is enthalpy here. Okay, so suppose we have a closed vessel like this. Okay, and we are applying some heat, so this heat would be at constant volume because we have a closed vessel, hence the volume of the vessel will not be changing, hence change in internal energy would be QV. And suppose we have a setup like this, we have a piston on a vessel or on a beaker. This is a piston. Okay, so here what will, if we are applying heat, so the pressure is constant because the piston's weight is not changing, but the boundary of the setup can actually move either up or down, and here the heat would be exchanged at constant pressure as the piston's weight is not changing, so that would be equals to change in enthalpy. Okay, and we actually defined two, we actually wrote two words here, CPM and CVM. So those are nothing but heat capacity per mole. So the unit would be nothing but joule per mole Kelvin. That's why we have multiplied this with N in both the cases. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing more on CPCV for an ideal gas. Okay, so till then, good luck and goodbye.